we're going to talk about what the graph of a geometric sequence looks like. I went back and picked 3 of the sequences that we just looked at and graphed them out for you. So I grabbed the illustration on page 1, that geometric sequence, then the geometric sequence from example 2, and the geometric sequence from example 3, and we're just going to look at their graphs here. Okay, so let's start with the illustration on page 1. If you go back to page 1 and look at this particular geometric sequence, that was this particular sequence 4, 12, 36, 108, 324, and so on. And so you can see in the graph, you can see the outputs here are the terms of the sequence 4, 12, 36, 108, and 324. Okay, so remember, the graph of the sequence itself are the red points, okay, these discrete points. Okay, I fit a curve to these points. Okay, so the blue dotted curve that you see going through the points, I fit that curve to the points so you can kind of see the trend that the points are following. Okay, I'm going to go ahead and write down the equation of this blue curve. It is 4 times 3 raised to the x minus 1 power. Okay, that is the equation of this blue dotted curve that's going through the discrete points. Okay, if you notice, okay, this is an exponential function. You've got x, okay, or n in this case. Maybe I should use n, okay, since we're dealing with a sequence here. The variable is in the exponent, okay? And if you flip back to this particular sequence, okay, we said the common ratio was 3. So if you look at this formula, look what the base of the exponential function is, okay? It's that common ratio, okay? And also, if you look at this, okay, 4, that's the number that's being multiplied out front. That is the first term. This is A1, okay? So what you're seeing here is that all of these points, the curve that's fitting these points, it's following this little trend of A1, the first term, times the common ratio raised to the n minus 1 power, okay? All right, moving on. Okay, let's look at the sequence that we saw in example 2. Okay, so if we go back to example 2, let's see where that was. That was back on page 2, I believe. Okay, oh no, page 3. So we go back to page 3, okay, and we're looking at this sequence in example 2. Okay, that was the sequence 6400, 1600, 400, 100. So this was a geometric sequence with a common ratio of 1/4. Okay, so again, I have plotted these discrete points of the sequence. You can see the outputs or the terms of the sequence. You see 6400, 1600, 400, 100, 25, and so on. Okay, I again fit a curve to these points. That's the blue dotted line. Okay, so you can see this is also exponential. Think back to section 4.5 when we looked at exponential functions. Remember, we graphed out e to the x and 10 to the x. It's the same kind of shape that we see here. Okay, so I again can fit the curve that I fit here. It has an equation. Okay, the equation here is 6400 times 1/4 raised to the n minus 1 power. Okay, so you're seeing the same kind of thing. Okay, when you look at this, this is exponential. The n value or the x value that is in the exponent that makes this exponential. It looks like an exponential curve, and you can see from this formula the base of the exponential function is r. Okay, remember the base is what's being raised to the power. Okay, out front we're multiplying by a number 6400. That's the first term in the sequence. Okay, so again, our curve here, all the points are falling along a curve that fits the bill of the first term times the common ratio raised to the n minus 1 power. Okay, Lastly, I wanted to show you the sequence in example 3. If you flip back to example 3, that was slightly different than the ones that we had seen before. And that was because, I'm trying to see if did I write out the terms of the sequence. I don't think I wrote out various terms of the sequence, but what was going on with this one, it had a negative R value. And so what happened was the terms would alternate. Okay. So if you have a geometric sequence where the signs alternate, if you graph it out, you're going to end up with something that looks like this. Okay. And the reason is because the signs alternate, you'll have a term that falls above the x-axis, and then the next term will go below the x-axis, and then back above, back below, back above. Okay, so the terms of this particular sequence in example 3 were 6, negative 18, 54, negative 162, 486, and so on. Okay, so what you see here, it looks like two exponential curves, one above the x-axis and one below the x-axis. And again, you're getting these two curves because of the alternating signs. One curve, the curve above the x-axis, is catching all the positive terms, and then the exponential piece that's below the x-axis, it's catching all the negative terms. Okay, so you're getting these two pieces here because of the alternating signs. Okay, if we didn't have the alternating signs, okay, everything would fall along one exponential curve here, and you would have the equation. Well, okay, here, let's do it this way. Okay, you can actually come up with two curves here. You can come up with a formula for the curve above the x-axis and then one for below the x-axis. The curve above the x-axis has the equation 6 times 3 raised to the x minus, well, I keep using x, it should be n minus 1 power. Okay, so again, this is, if you look at this, the R value is 3. Okay, so that's your common ratio value. Okay, and I know when we actually did the problem, we had R was equal to negative 3. Okay, but to fit this curve here, I need to make it positive 3. Okay, and A1, this is the first term. Okay, and let me say this is R, like I said. Okay, if you just do a reflection about the x-axis, you will get the curve below the x-axis. So if you remember your transformation rules from algebra, all you have to do to reflect a curve about the x-axis is put a negative sign out front. So this curve below the x-axis has equation negative 6 times 3 raised to the n minus 1 power. Okay. All right, so what we see from all of this, okay, we're going to make some conclusions. We did the same thing for arithmetic sequences. Okay, let's look below. Conclusion number 1, the graph of a geometric sequence is an exponential function. Okay, again, the graph itself consists of discrete points. Okay, those blue curves that I fitted to the points, that's not actually part of the graph. I was just showing you the trend of the points. Okay, the discrete points make up the graph, and so that means the domain is a subset of the natural numbers. Always for a sequence. Okay, so the graph of a geometric sequence is an exponential function whose domain is a subset of the natural numbers. Okay, conclusion number 2, the common ratio is the base of the exponential function that you're dealing with. Okay, we saw up here, we plotted all our points. I fit a curve to each one. It was an exponential curve. The n value or x value, however you want to look at it, is located in the exponent. The base of each exponential function was the common ratio. Okay, and then lastly, a geometric sequence can be recognized algebraically because its formula will have this format. Okay, we said that when we looked at these blue curves, the trend they were following was this. Okay, the first term times the common ratio raised to the n minus 1 power. Okay, so I'm going to write that down a1 times the common ratio raised to the n minus 1 power. Okay, so if you are going through this and you see a sequence or a series that looks like this, a number times another number raised to the n minus 1 power, you know automatically that that's geometric. Okay, it was just like recognizing arithmetic. Arithmetic fit the bill of mx plus b. Okay, you're going to be able to recognize geometric as well. Okay, it could come in another format. Okay, watch this. I'm going to do something a little mathematical here. I'm going to take a1. Okay, if you have r raised to the n minus 1 power, you can break it up this way. This is the same thing as r to the n times r to the negative 1. Okay, that's going to be a1 times r to the nth power over r if I get rid of the negative exponent. And then r is just a number, it's the common ratio. We can combine these two guys, a1 divided by r, and that will give us another number. I'll just call it a. It's not a1, it's a different number, times r to the n. So you may see the formula come through this way. Just a number, it's not a1, but it's a times r to the n. Okay, so again, you're recognizing these geometric sequences algebraically because you see the n value located in the power or the exponent.